Imagine one Bitcoin address spendable 5 different ways: by Alice today, by Bob tomorrow, by any of 3 after a month, by a lawyer after 90 days. One locking script, and the spender chooses their path. The trick is a stack-based if-else that, at first glance, looks backward. Bitcoin script is a stack-based language with 4 flow control opcodes. Op-if pops the top stack item and runs the next block if it's true. Op-else marks the alternative block. Op-endif closes the conditional. Op-notif is ops-if with the test inverted. Recall that an opcode is a single script instruction, and a UTXO, an unspent transaction output, is locked by a script that the spender must satisfy. These 4 opcodes are how that lock branches. Stack-first thinking is the key. In Bitcoin script, operands come before operators. The expression 1 OP ID pushes 1, then OP ID pops both and pushes 2. Conditionals work the same way. The true or false flag must already be on the stack before OP-if executes. OP-if pops that flag and chooses a branch. The condition isn't written inside the if block like in Python or C. It's pushed onto the stack first. Here's the simplest branching contract. The locking script reads op-if, Alice's pub key, op-else, Bob's pub key, op-endif, op-checksig. Whoever spends supplies an input script, also called the scriptSig. Alice unlocks with her signature followed by op-true. Bob unlocks with his signature followed by op-false. The locking script is the menu of possibilities. The input script is the order. Notice that op-true goes last in Alice's input, which means it lands on top of the stack, ready for op-if to pop. Stack order matters because the last thing pushed is the first thing seen. Let's walk Alice's spend through the stack. Push her signature, stack hold sig, push op-true, stack hold sig, then true on top. Op-if pops true and enters the if branch. Push Alice's pub key, stack hold sig and pub key. Op-else skips Bob's branch. Op-endif closes the block. Op-checksig pops pub key and sig, verifies the signature, pushes true. The transaction is valid. If Bob had supplied op-false instead, op-if would have skipped to the else branch and pushed Bob's pub key instead. Now what if we don't need an alternative path? Just a guard clause that aborts on failure. That's where verify opcodes shine. Consider op hash 160, then a hash, then op equal verify, then Bob's pub key, then op checksig. The spender provides a pre-image, the secret value that hashes to the stored digest, plus Bob's signature. Equal verify checks the hash and immediately aborts if it doesn't match. No else branch. Compare this to an op-if version. Same logic, but you'd add an explicit op-true comparison and an endif. 2 more opcodes, more bytes, more fees. Rule of thumb. Use verify when failure should kill the script. Use op-if when you genuinely have alternative branches. Conditionals nest. Picture a binary tree. The root is an outer op-if. Its true branch contains an inner op-if, which itself splits into subscript A and subscript B. The outer false branch holds subscript C. To reach subscript A, the spender supplies true. Outer if takes true. Inner if takes true. To reach subscript B, supply true false. Outer if enters its true branch. Inner if takes false. To reach subscript C, supply just false. Outer if jumps to its else, and the inner conditional is never executed. Stack order is everything. The flag pushed last is consumed first, so the spender writes flags in reverse navigation order. Let's trace reaching subscript B with input flags op1, op0, push true, then push false. After both pushes, the stack holds true on the bottom, false on top. The outer op-if executes first. It pops the top, which is false. Wait, that sends us into the else branch towards subscript C, not B. So to reach subscript B, we actually need to push false then true. putting true on top for the outer IF and leaving false underneath for the inner EF. This is the most common nesting bug. Always read your flag stack from the top down, matching opcode execution order. One quick aside before our finale. You'll often see OP0 prepended to multisig input scripts. New learners assume that 0 is the first signature slot. It isn't. OP check multisig has a famous off by 1 bug. It pops 1 extra value from the stack and discards it. That dummy 0 is just feeding the bug. Knowing this saves hours of debugging when you're handcrafting multisig spans. Now let's combine everything, nested IFs, verified style guards, and time locks, into a real contract. Mohammed runs a small company and wants 1 Bitcoin output with 3 spending parts. Part 1. Daily operations. Any 2 of 3 partners sign instantly. Part 2. Recovery if a partner is unreachable. After a 30-day relative time lock, 1 partner plus the company lawyer can spend. Part 3. Last resort. After 90 days, the lawyer alone can recover funds. The locking script wraps these in nested conditionals. The outer OP if splits fast paths from slow paths. Inside the fast branch, an inner OP if chooses between 2 of 3 multisig and the 30-day recovery. The outer else holds the 90-day lawyer-only path. Time locks use OP check sequence verify, the relative time lock opcode, which aborts the script if the spending transaction is broadcast too early. To trigger pass 1, partners supply their signatures and flags true true. Pass 2, lawyer plus partner sign, flags false true, and they must wait 30 blocks worth of time. Pass 3, lawyer signs alone, flag false after 90 days. Notice how each leaf uses verify for the time lock. Failure should abort, not fall through. While OP if separates the genuine alternatives. That's the design rule in action. Step back and see the pattern. A UTXO isn't a single lock, it's a tree of locks, and the spender navigates that tree with flags. Op if gives you genuine alternatives. Verify gives you efficient guards. Time locks gate parts by time. Nested together, they encode contracts with dozens of redemption routes, all enforced by consensus, no off-chain trust required. This is the conceptual ancestor of mini-script and taproot script pads, where complex policies compile down to exactly these primitives. Once you see UTXOs as decision trees, Bitcoin smart contracts stop feeling mysterious.